For lesson 7, we're going to look at trigonometric identities. This is just a little introduction to identities. You will probably see a lot more of this in grade 12 advanced functions, but for now, there are a number of equations involving the trigonometric ratios that are true for all values of theta. These equations are called identities. So we're going to have a table. Usually you'd get this on a formula sheet. These are identities that we kind of just take for granted that they are true. Some of these you maybe haven't seen. This is called cosecant. So they're just saying cosecant of an angle is actually the reciprocal identity. So cosecant of an angle is the same thing as 1 over sine theta. Secant is the same thing as 1 over cos theta, and cotangent is 1 over tan theta. So these are just special names for the reciprocals of the trig ratios that we already know. And then we have some quotient identities. So tan theta is the same thing or equal to sine theta over cos theta. It would make sense then cotangent is the reciprocal of tangent. So we would have that upside down. I'm going to take a minute and maybe just talk to you about why this one is true and why, just with the math that we already know, could we prove that. Also, Pythagorean identities, dealing with the Pythagorean theorem. Sine squared theta plus cos squared theta actually equals 1. And then these are just different versions of that same sort of main Pythagorean theorem identity. I might take a minute and also prove to you why that is true. Reflection identities, this might make sense if we just imagine a Cartesian plane and we had an angle that was theta. The sign of negative theta, so negative theta would come down this way. The sine of that angle would equal negative sine theta because of our cast rule, we know that sine is negative in this quadrant. Same goes with cosine. If we had negative theta, your angle would be down here in this quadrant where cosine is actually positive. So let's just take a second and look at these two identities just to kind of show you what this represents. So the first one we'll look at is this one, and we just kind of have to take for granted that whatever is in the chart is true. But if you were wondering why this is true, let's imagine a right triangle with angle theta. So if that's our angle of reference, this would be our opposite, and this would be our adjacent, and this would be our hypotenuse. But this is just a regular triangle, so let's call this side A and B, and then C for the hypotenuse. In order to prove an identity, what we would take is the left side first is tan theta, and then the right side is sine theta over cos theta. And we're trying to show that the right side, which is a little more complicated, actually equals the same thing as tan theta. So tan theta, for our purposes here in our triangle, that would actually equal opposite over adjacent. So that would equal A over B in this case. On the right-hand side, sine theta would be opposite over hypotenuse, which would be A over C. And then the cosine of theta would be B over C, adjacent over hypotenuse. So I really don't like fractions when they're written like that. Maybe I'd write this as A over C divided by B over C, because then it helps me remember that I would invert and multiply. So our C's could cancel out and we end up with A over B, which is the exact same thing as what we had on the left side. So we know, therefore, tan theta equals sine theta over cos theta. We're going to use these types of identities to simplify other work that we have. So they will be useful, but I didn't want to just state something without showing you why it might be true. The main Pythagorean theorem identity that we see is sine squared theta plus cos squared theta equals 1. And we will use this to simplify other work that we have. So let's imagine again that we have a right triangle and we have sides A, B, and C being the hypotenuse. If we break our identity into a left side and a right side, the left side is sine squared theta plus cos squared theta, and the right side equals 1. How can we prove that the left side actually equals the right side? We can look at our triangle over here. I know that sine of an angle here, angle theta, would be opposite over hypotenuse, so that would technically be A over C, but that would be squared. And cos squared theta would be adjacent over hypotenuse, or B over C, but that would be squared. So when I try and simplify a little further, I can square the numerator and the denominator for both. And then I can add up my numerators, a squared plus b squared over c squared. And I just have one denominator. But if we think about the Pythagorean theorem, that's why this is called a Pythagorean identity, a squared plus b squared, we know the Pythagorean theorem, it does equal c squared. So the numerator could be c squared, the denominator is c squared, and that equals 1. So our left side equals our right side, and we've come up with one way to prove that sine squared theta plus cos squared theta equals 1. So we have this table, and I usually include that on formula sheets. It's just something that you'll use quite a bit to refer to. There are ways to show that all of these identities are true. So some strategies for proving identities. We just proved 2 identities that we saw in the table. We're going to use those, though, to help us prove other identities. So simplify one side at a time. Start with the more complicated side first. That would be a good thing to do. If you see a complicated side, you're trying to make it look like the simpler side and make the left side look exactly like the right side. When you see reciprocals like cosecant, secant, or cotangent, or even just tangent, we usually like to express everything in terms of sine theta or cos theta. That's probably going to get you further along when you're trying to simplify. Simplify algebraically using common denominators or factoring. So we are going to assume that you have these skills already, and you're going to also pull out whatever skills you need to solve your problem. So when sine squared theta, cos squared theta, etc. appear, use the Pythagorean identity if the use of the identity simplifies the expression. So there is one big difference, though. Let me just say, you might have some questions maybe in your homework that just say simplify. So if your question just says simplify, we're trying to write this in as simple a form as we can. So we would leave our sine theta because that's good. Cosecant is actually the reciprocal of sine. So we would write that as 1 over sine theta. From our identity chart up above, cosecant is here. So I might write cosecant theta as 1 over sine theta. And what happens then is that these would cancel and I actually just get 1. So I have simplified. I'm not trying to prove the left side equals the right side because there is no left side and right side. I'm just trying to simplify as much as I can. Example 1, though, says prove. So we want to show that somehow our left side equals our right side. So one strategy, when we have a more complicated side, we're trying to make maybe the left side look like the right side. So I want to prove that the cotangent of theta times the secant of theta is the same thing as the cosecant of theta. So when I look up to my chart, cotangent is the same thing as cos theta over sine theta. So maybe I'd like to write that as cos theta over sine theta. And secant of theta, when I look up here, secant is actually the same thing as 1 over cosine theta. You can see that we're able to cancel out cosine theta, and I'm left with 1 over sine theta. Now you could express that as cosecant theta, because that is the same thing. That's the reciprocal of sine theta, and you've proven that the left side equals the right side, so the identity is true. A little hint, most of the time teachers are going to give you questions where the identity is true because we are trying to get to a point where we can show that the left side equals the right side. You might work all day trying to show that an identity is not true. That's way more vague in order to show that, because you might try many different things and never get the answer that you're looking for. So yeah, the questions that you're going to be given, the identity will be true. You just have to come up with a strategy in order to show that. So part B, if we look at tan theta times cosecant theta, and we're saying that that equals secant theta, we have to prove that this is true. So we break it up into left side and right side. And one of the things that we're suggesting is that you always try and tackle the more complicated side first. Let's try and make the left side look like the right side. So tangent is the same thing as sine theta over cos theta. And I know that cosecant is the same thing as 1 over sine theta. It's the reciprocal of sine theta. Again, I can pretty easily see that these would cancel out. I'm left with 1 over cos theta, and that's the same thing as the reciprocal. So we have our reciprocal identity. This is the same thing as secant theta. So again, we've shown the identity is true. And part C, we have another cotangent theta divided by cosecant theta. Try and prove that that actually equals cosine theta. So we're going to tackle the left side first. I know that cotangent theta is the same thing as cos theta over sine theta. And I know cosecant theta is the same thing as 1 over sine theta. It's the reciprocal. So another way to write that big fraction is to use a division symbol. So cos theta from the numerator over sine theta is divided by 1 over sine theta. But then we know we should invert and multiply. So we multiply by sine theta over 1. And we end up being able to cancel our sine theta, and we have cosine theta. And again, we've proven the identity to be true. Example 2 is another question where we're asked to prove the equation. So you can start just with breaking these up into left side and right side. When I look at the chart, I do see that cosecant squared theta equals 1 plus cotangent squared theta. But then I also have the minus 1 at the end. So what this simplifies to look like pretty quickly is cotangent squared theta. So I could keep going and I can get that into tangent, I could get it into sine and cosine, but I also sometimes just want to see if I can get the right side to look like the left side. So cosecant squared theta is going to be the same thing as just cosecant theta squared, which would be the same thing as 1 over sine theta squared, or we could write it as sine squared theta like that. The entire thing could be squared, which means 1 times 1 is still 1. And then we multiply by cos squared theta. And what that means is that we have cos squared theta divided by sine squared theta. And hopefully you're understanding that I could write it as cos theta over sine theta squared. Hopefully you see that is actually the same thing. So I could say that this is also, when I look at cos squared theta over sine squared theta, or cos over sine is cotangent, but in this case it would be squared. So we have cotangent squared theta. And I end up arriving at the fact fairly quickly that the left side equals the right side, and that's all I need to prove, is that the left side equals the right side. I could have gone a little further with the left and then also a little further with the right, to make them maybe look like they're in terms of sine and cosine, but I have proven this identity to be true. So we have a couple more. We have more fractions. These are going to get more and more complicated as we go. So when I look now at my left side and my right side, I am going to focus a little bit more on trying to get everything I see written in terms of sine or cosine. So a true left side, right side check like this, you always want to make sure that you rewrite the left side exactly how it was and the right side, rewrite it first and then move on from there. So I know that tan theta is the same thing as sine theta over cosine theta. And I also know that cotangent is the same thing as cos theta over sine theta. I could get a common denominator in the numerator, which would be cos theta for both. So if I had to multiply the left here by cos theta, I would have cos theta over cosine theta plus sine theta, and then I have a common denominator. Same with the bottom. Maybe I would make this sine theta over sine theta so that I'm able to have a common denominator of sine theta. This would really be division, so cosine theta plus sine theta divided by cosine theta divided by, so this is a division symbol, and then I can invert and multiply. And what we see is that the numerator over here and denominator are the same. So I end up with sine theta over cos theta. And now we want to see if we can get the right side to look the same. So I think my strategy would be the same. I would like tan theta to be written as sine theta over cos theta. And cotangent could be cosine over sine. I get my common denominators. And I might try and skip a step here. And then I would invert and multiply. And again, I notice that my numerator and denominator could cancel out. And I have sine theta over cosine theta. So I have proven this identity to be true. Obviously, with this last question, the right side being just tan theta looks pretty simple. I would just leave that. On the left side, I would like it to eventually look like the right side. So a good strategy is to write what you have in terms of sine and cosine. So maybe I would start with sine over cosine is the same thing as tan theta. And then I do have cosine theta plus 1 in the denominator. In the numerator, I would like a common denominator. So what that means is if this was sine theta over 1, I would have to multiply sine theta by cosine theta in order to get a denominator in the numerator of cosine theta. I might then just write this as divided by the cosine theta plus 1. Now this is the first time we might see some factoring. I see what is common to both terms is sine theta. I can factor out sine theta and I would be left with cos theta plus 1. I can also invert and multiply. If this is over 1, now I can invert and have cos theta plus 1 in my denominator. Since I'm working with a lot of multiplication here, I'm able to cross these terms out, these terms that are alike, and I end up with sine theta over cosine theta, which really is the same thing as tangent theta. I can finish off like that, showing that the left side equals the right side, or I could leave it as sine theta over cosine theta, but we're trying to simplify as much as we can. And in my opinion, tan theta looks more simplified than sine theta over cosine theta. So the left side equals the right side, and we've proven this identity to be true.